following movie, we'll create a multiphysics fluid structure model of a wing flap assembly. We'll begin with a JT file of the assembly. I've chosen a JT file as a CAD neutral format to show the capabilities of Simcenter 3D to work with neutral CAD format data, specifically JT, because of some associative capabilities that it has. We'll begin creating our simulation models in the multiphysics coupled flow structure environment. And we'll create a couple of we'll create a solution for the stowed configuration. Here we can pick our favorite turbulence model. And we'll create a solution step. Create two steps, first one being at time 0. This will be a transient analysis as well. Then we'll create a second step at time 20 seconds. And with a 10-second step size, that will give us two time steps, and we want to make sure that we recover results at both of those times. All right, so we'll begin idealizing our model. We'll create an associative copy of some of the geometry that we'd like to modify. And then we'll use the synchronous modeling tools to make some modifications. We'd like a sharp trailing edge on our airfoil surfaces, so we'll go ahead and do that. And there's another trailing edge that we'd like to modify down here. Deleting the face doesn't work for this one, so we'll move the face with the move face command. And that creates our sharp trailing edge. All right, now that we've done that, let's go ahead and create the air volume for our flow simulation. And we'll create that by sketching a rectangle which will encompass the air volume. And we'll extrude that rectangle and then subtract out the airfoils from it. All right, just to reduce the size of this air volume, we'll go ahead and throw some edge blends on it. And next we'll mid-surface the forward frame, because we'd like to put a shell mesh on it. Now that we've mid-surfaced it, we'll bring it in to the FEM, where we'll mesh it. All right, now we'd like to ensure that we get a congruent mesh on the entire part. So to do that, we'll stitch the edges together. And here you can see the free edges in magenta. And it's just stitched the edges together to ensure we'll get a congruent mesh. Next we'll go ahead and mesh it with linear quadrilaterals. Add a element size of 0.2. All right, and there you can see our shell mesh. As a double check, we can display the free element edges in the mesh, and it will be displayed in magenta. If we turn off the geometry, you can see that a little more clearly. All right, so that looks good. Next, we'll assign a material to the mesh collector. And this particular forward frame we'd like to make out of titanium alloy. So we'll pick one out of the library. You can create your own materials and your own libraries as well. Now we won't assign a thickness. The way that we'll assign the thickness is by inheriting it from the mid-surface definition. So this is a way that we can reduce the error with defining our model. You can see it's inherited the thickness in the various regions on the forward frame. All right, then we'll go ahead and save a layout so that when we come back to the FEM, we'll see that same view. All right, next we'd like to brick mesh our link number 4 here. So we'll get an associative copy of it, and then we'll go ahead and split it because it doesn't look like we'll be able to brick mesh it the way it is. But we can check for sweepable bodies right within the split body command. It will color things green that it knows that it can sweep, and red things that it doesn't think it can sweep, and yellow things that it's not sure. So we changed that from red to green, so we're good to go for sweeping that one. Let's go ahead and bring it in to the FEM along with the rest of the links and frames and airfoils. Let's make sure we're selecting solid bodies this time. And we don't need some of the pins that mount the mid frame to the forward frame. We're going to be modeling those with 1D connections a little bit later on. All right, so now to ensure we'll get a congruent mesh between the frame and the airfoil, we'll go ahead and create a mesh mating condition. And the same thing on the link. We want a congruent mesh across those two parts of the link that we split up. So we'll create a mesh mating condition there as well. All right, now we'll go ahead and brick mesh link number 4. Just so you can see what's going on a little bit better, we'll just work with the bottom part of that. And you can see it's got two faces. Those two faces were created when we created the mesh mating condition to ensure that we get a congruent mesh. And we can go ahead and sweep from those two faces to one single target face. We'll assign a source element size and go ahead and mesh it. All right, so that looks good. We'll show all. I have a hotkey to show all. Bring back the rest of the bodies. And we'll mesh the top part of it with not fluid hexahedrons, but linear structural hexahedrons. But it looks like we incorrectly meshed the bottom part of the link with fluid hexahedrons. We'll go ahead and edit that mesh to correct that. So now we have a structural mesh on there instead of a fluid one. Get rid of that fluid mesh collector. And now we can go ahead and mesh the top of our link. And we'll put it into the same mesh collector so that we can assign the same material to it. You can see we've got a congruent brick mesh there. And we'll make this out of titanium as well. And we'll name the collector after the material. Alright, next we'll put a tetrahedral mesh, parabolic tetrahedrons on the rest of the links and the frames. Go ahead and do that all in one shot here. And because we want different element sizes on different links based on how large or chunky they are, we'll use the auto size per body option, and we'll also mesh them all into the same titanium alloy collector, so the material will be assigned to all of those meshes. Alright, so there you can see how it's put a slightly coarser mesh on some of the frames, and the links are meshed more finely. Alright, next we'll put some 1D connections between the forward frame and the links. And we'll start by creating some rigid spiders. And we'll select the type rigid link to create those rigid spiders. Point to edge. These are all geometry-based meshes. And that's important so that we'll be able to update our CAD model and FE model to those changes. So now we'll create point to face 1D connections to complete the connection between the forward frame and the links. Alright, that looks good. Let's next connect all of our links with surface-to-surface glue. And there's many links, there's many places where they're connected. We have an automatic pairing algorithm that we can use by just selecting all of those links and mid-frames and tell it to find the face pairs within the tolerance that we specify and create the glue. That greatly simplifies the process of connecting a complex assembly. Here we'll go ahead and make those markers a little bit smaller, they're a little bit large. Alright, that looks good. Now we'll put some structural constraints on our forward frame. And we'll also put a structural constraint on our mid and aft airfoils for symmetry. Alright, we'll save a layout so we can come back to this view next time we open up the sim. Alright, now we'll bring in the air. And so that we have a congruent mesh between the airfoils, the mid and aft airfoils, and the air, we'll go ahead and create a mesh mating condition there as well. A congruent mesh is not required, but does reduce the resources required to solve. All right, here we'll put some mesh controls around the forward airfoil to refine the fluid mesh that we'll be creating in just a moment. Next, we'll put some additional mesh controls on our airfoil surfaces. To control the mapped mesh that we'll create on it of parabolic quadrilaterals. We'll put that into a new collector. Select an element size and go ahead and mesh it. We'll go ahead and update the connected 3D meshes. Alright, that looks good. Let's go ahead and mesh our air now. This time we'll sweep fluid linear hexahedrons with a source element size of 2 into a new collector. And we'll assign air as the material property for the fluid. Alright, so that looks good. Let's now go back to the sim and we'll assign some fluid boundary conditions. Here we'll create a flow boundary condition. This will be an inlet, and we'll specify an inlet flow that will be time dependent. And we'll also specify the units for that variable as miles per hour. So at time 0 will be at 0 miles per hour, at time 10 seconds will be at 50, and also at 20 seconds will be at 50 miles an hour. All right, next we'll specify another flow boundary condition. This one we'll specify as an opening, and we'll go ahead and select the 3 aft faces there. Next we'll specify our flow surfaces. We'll specify boundary flow surfaces for the forward airfoil. And this fluid structure interaction will be none, because there's no structure there to couple to, and we'll use a wall function for the wall treatment. However, for the aft 2 airfoils, we'll specify a boundary flow surface, and we'll use the tangent face selection there, as well as the quick pick to pick inside the part. We'll couple the fluid and structure, and also specify a wall function. All right, so next we'll go ahead and select the 2 sidewall faces, and we'll specify a symmetric symmetry plane. For the flow. All right, then we'll save, and we're almost ready to solve, but we forgot, I think, one thing with our mapped mesh that we created on the aft 2 airfoils. We didn't select a material, and this we'd like to make out of aluminum 6061, and we'd also like to specify a thickness, because we didn't create a mid-surface there, so we can't inherit the thickness. So we'll put the thickness on the physical property in the mesh collector. All right, so now we're ready to solve. And I'll pause the movie, but you can see in the bottom right-hand corner of the solution monitor the elapsed time. And we have some nice monitors where we can see the progress of the solution and interim results. And here you can see the total elapsed time as it's completed is 1 minute and 20 seconds. All right, so now we're ready to look at the results, and because this is a multi-physics solution, we have two sets of results. One is the flow results and the other is the structural results. We'll look at the flow results first at the last time step, 20 seconds, and we'll look at the velocity of the flow, and we'll look at that as an arrow plot. It's a little easier to see with solid style arrows and with our mesh off and just looking at the feature lines there. All right, so there you can see the magnitude and direction of the flow. You can also visualize this as a streamline. Here I'll specify some seed point locations for our streamlines. And this result can be animated with some virtual particles traveling along those streamlines. All right, let's also take a look at the pressure on our flow surfaces. So here you can see this will be passed to the structural solver, which is done automatically as part of the multiphysics solution. So next let's take a look at our structural results, also on the last time step, when the 50 mile an hour inlet is being used. And here you can see our maximum displacement. And you can also take a look at our stresses. And by turning on the annotations, you can see where the maximum occurs and what that is. Here you can see it's somewhere around 22 KSI average stress. Looks like we need to maybe beef that area up a little bit. Also, link number 4 looks like it has some relatively high stresses. Maybe if we reduce the pocket depth of that link, that will help to strengthen it. And then also there's a very thin web in the mid-frame here. It's a little bit difficult to see, but right in this area there's a thin web. There you can see it. So there's a few changes we'd like to make. The first change will be made from the native CAD authoring system, and an updated JT file has been created of the change to link number 4. And in order to incorporate that change, we need to first close our CAD assembly. We just have the FE assembly open right now. And here's our link number 4, and the JT file stays associatively linked to our CAD part file. So we'll rename it to the original and then rename the changed 4A to just 4, so that when we open our CAD assembly, it will look to that updated JT file and it will update our link number 4 in our finite element model assembly. So here you can see the CAD has been updated. That pocket is much shallower now, but the finite element model doesn't reflect it until we hit the Update FE Model button. And now you can see our brick mesh has updated. It's maintained the congruent mesh and the mating conditions that we'd created, we'll make our next two changes using Simcenter 3D and the synchronous modeling capabilities. Here we'll extend the slotted portion all the way down to the frame to strengthen it. And then we'll also extend another face in our midframe to strengthen it, to eliminate that thin web area there. All right, so now that we've made those two CAD changes, we'll go back to our finite element model and we'll update the mesh. And just so you can see both of those regions, I'll try and orient the view such that you can see both the thin area there that we just updated as well as the slot that we extended. Go ahead and update the mesh there. And it maintains all of the material properties, the connections that we've made, the fluid boundary conditions. Everything stays associatively linked. We don't have to start over from scratch again. Just hit the update button and we're ready to solve. So that I can maintain the original results, I'm going to first clone that solution so that it won't overwrite my original results. And we'll call this clone solution stowed 2. And then we'll go ahead and solve it. This way we'll be able to look at our results side by side. I've paused the movie here. You can see in another minute and 17 seconds we have updated results, which we'll take a look at now side by side with our original results. So here we'll begin by looking at our structural result from our original configuration, and we'll put that on the top. Then we'll open our changed configuration on the bottom. We'll go ahead and link the views, so when we rotate or zoom one, we'll be doing that to both. And here you can see our maximum displacement has been substantially reduced. You can see it still occurs in the same location, but we've reduced it by over 30%. Next, we'll take a look at our stresses. And here you'll see a much larger difference. You can see we've gone from 22 KSI to less than 10 KSI, closer to 9, so that's a 50% reduction there in stress as well. All right, so we're able to quickly and easily make changes and evaluate the effect of those changes on our simulation model. All right, the next change we'd like to make is to deploy the flaps. And the way we're going to do that is by defining assembly constraints between the various components in the assembly. We'll start by fixing the forward frame, and then we'll put relationships of aligning the various components. So this will infer the central axis between the various cylindrical faces that we're selecting. This next one's a little bit hard to see, but we can sort of see it through there. All right, now that we've completed the specification of the first central axis constraints, we'll go ahead and put a distance constraint on our slot here on the aft frame. and that distance is 0. All right, now that we've established our assembly constraints, if we were to move the driving link, we'll be able to deploy the flaps. So here I'll move it. We'll specify some handles that will be at the center of that axis there. And we'll go ahead and rotate it. All right, so now our flaps are deployed. Let's go ahead and update our Multiphysics model to reflect the deployed flaps. All right, so here you can see the CAD is updated. If we take a close look at that trailing airfoil, it's getting very close to the end or the edge of our air volume. Let's go ahead and tweak the air volume's location. Let's go ahead and move that a little bit aft. So we'll go back to the sketch that we had created to define that air volume, and we'll just drag it. And that should be good right about there. All right, so let's go ahead and update our simulation model. Now I have a little bit more leeway there. Let's go ahead and update. And that updates our structural and fluid models. All of our fluid and structural constraints have survived the update, and we're ready to solve. I'll go ahead and clone this solution as well so we can maintain those original results from our stowed 2 configuration. We'll call this one deployed. We'll solve. I'll pause the movie, and you can see in another minute and 25 seconds we have our updated results for our deployed configuration. And we can take a look at those results as well. Here you can see our structural displacements are quite a bit larger because the aero loads are much larger on the flaps, and it could also be due to the structural arrangement of the links being different. And here we can also see our stress results. And we can look at the average result. You can see the location of the maximum and the maximum value. And its location. And we can also compare that to our stowed configuration as well. We can bring up our stowed configuration for comparison to see how those stresses compare. All right, so there you can see how the stresses have increased by deploying the flaps. So Simcenter integration of JT, assemblies, structures, computational fluid dynamics enables rapid analysis of complex assemblies with multiple performance requirements.